Today we're going to explore one of the most fascinating intersections of thermodynamics, information theory, and microfluidics, Maxwell Demons and lab-on-a-chip devices. First, let's understand what a Maxwell Demon is. In 1867, James Clerk Maxwell proposed a thought experiment that seemed to violate the second law of thermodynamics. Imagine a box divided by a partition with a tiny door. A demon operates this door, allowing only fast molecules to pass from left to right and slow molecules from right to left. This would spontaneously create a temperature difference, apparently decreasing entropy without doing any work. This seems to violate the second law of thermodynamics. The resolution to this paradox came much later. The demon must measure the speed of each molecule, store that information, and eventually erase it. This information processing has a thermodynamic cost. In 1961, Rolf Landauer proved that erasing information has a fundamental thermodynamic cost. This is known as Landauer's principle. Erasing one bit of information requires dissipating at least kBt natural log of 2 of heat, where kB is Boltzmann's constant and T is temperature. At room temperature, that's about 2.87 times 10 to the negative 21 joules per bit. This seems tiny, but it adds up. So the demon's information processing generates entropy that exactly compensates for the apparent entropy decrease in the gas. The second law is safe. Now let's jump to modern technology. Lab-on-a-chip devices can implement real Maxwell demons using feedback control and selective forces. The first example uses feedback-controlled microvalves to sort particles. A camera detects particles flowing through a microchannel. When a small particle approaches, the valve directs it upward. When a large particle approaches, it goes downward. Here's the key point. No net mechanical work is done on the bulk fluid. The valve simply redirects flow that's already happening due to an external pressure difference. Yet the system sorts particles, creating order from disorder. It separates a mixed population into two sorted populations, decreasing entropy locally. So where does the thermodynamic cost appear? Let's trace the information flow. Step 1. The camera measures each particle's size. This creates information about the particle. Step 2. A computer processes this information and decides whether to open or close the valve. Step 3. The valve actuates based on this decision. Step 4. The memory must be erased to prepare for the next particle. This is where Landauer's principle comes in. Each sorting decision generates at least kB natural log 2 of entropy in the information processing system. Let's do a numerical estimate. Suppose we sort 1 million particles per second. The minimum power dissipated is n times kBt natural log 2, where n is the particle rate. That's 1 million times 1.38 times 10 to the negative 23 times 298 times 0.693. This gives about 2.85 femtowatts. That's incredibly tiny, but it's the fundamental lower bound. Real systems dissipate much more than this because cameras, processors, and valves are far from thermodynamically reversible. Typical systems might use milliwatts or even watts. The second example uses light-driven forces to sort particles without mechanical valves. A focused laser beam creates a local temperature gradient. Particles experience thermophoresis, a force that pushes them along the temperature gradient. Different types of particles have different thermophoretic mobilities, so they move at different speeds in response to the same gradient. By selectively illuminating certain particles based on feedback from a camera, we can sort them without any mechanical contact or bulk fluid work. The thermophoretic velocity is negative dt gradient of T, where dt is the thermophoretic mobility. The laser does work on the thermal field, heating the fluid locally, but it doesn't do direct mechanical work on the particles. Let's carefully account for entropy in this system. Where does entropy increase to pay for the sorting? The particles become more ordered after sorting, so their entropy decreases. This is negative. The bulk fluid returns to its original state, so its entropy change is approximately 0. But the laser dissipates energy as heat. This generates entropy in the surrounding thermal bath. And the information processing system generates entropy according to Landauer's principle. The total entropy change is the sum of all these contributions. The second law requires this to be positive, and indeed it is. Here's a key question. Can we ever beat the Landauer limit in practice? In principle, we could use reversible computing to approach the Landauer limit, but real devices are far from reversible. The measurement process itself is highly irreversible. Photons scatter off particles, cameras convert light to electrical signals, all generating excess entropy. The ratio of actual energy dissipation to the Landauer minimum is typically 1 part in 10 billion or worse. Despite the thermodynamic costs, these systems are incredibly useful. Let's look at some applications. Cell sorting is crucial for medical diagnostics. We can sort rare cancer cells from blood samples, separating one target cell from millions of normal cells. In drug discovery, we can sort cells based on their response to different compounds, identifying promising drug candidates. In synthetic biology, we can sort engineered cells based on their behavior, selecting for desired traits. We can separate nanoparticles by size, shape, or composition for material science applications. To understand the thermodynamics more deeply, let's consider the Szilard Engine, a simplified Maxwell Demon. Step 1. A single molecule is in a box. We measure which side it's on. This costs no energy in principle if done reversibly. Step 2. We insert a piston on the left side and let the molecule push it to the right, extracting work equal to kBt natural log 2. The work extracted is exactly kBt natural log 2. Step 3. We must erase our memory of which side the molecule was on. This requires dissipating at least kBt natural log 2 of heat. The heat dissipated in erasure is at least kBt natural log 2, exactly canceling the work we extracted. The net result is zero useful work. The second law is preserved because information erasure pays the thermodynamic bill. How does this connect to our lab-on-chip systems? The principle is exactly the same. Every time we sort a particle, we're essentially running one cycle of a Szilard engine. We measure, make a decision, and then erase the memory. This beautiful connection between information theory and microfluidics shows that information is physical. It has thermodynamic consequences. These principles have profound implications for biological systems. Cells are constantly sorting molecules and maintaining organization. In a sense, cells are Maxwell Demons powered by ATP hydrolysis. They use chemical energy to measure, decide, and sort molecules. ATP hydrolysis releases about 50 kilojoules per mole of free energy under cellular conditions. That's about negative 8.3 times 10 to the negative 20 joules per molecule, which is about 20 kBt at room temperature. This is far more than the Landauer limit of kBt natural log 2. Biology is not thermodynamically efficient, but it's effective. Motor proteins like kinesin and myosin use this energy to transport cargo in specific directions, sorting molecules within the cell against their concentration gradients. For those interested in deeper theory, fluctuation theorems provide a more complete picture of these processes. The Crookes fluctuation theorem states that the probability of observing a negative entropy change A relative to a positive entropy change A is exponentially suppressed. This means transient violations of the second law are possible, but they become exponentially rare for larger entropy changes. For lab-on-chip systems, this means occasional sorting errors are thermodynamically inevitable. Perfect sorting would require infinite energy. Let's discuss some practical design considerations for building these systems. There's a fundamental trade-off between sorting speed, accuracy, and power consumption. Faster sorting requires more power and generates more errors. Optimal control strategies can minimize dissipation by operating close to thermodynamic reversibility, but this requires very slow operation. Practical systems use parallelization, running many sorting channels simultaneously to increase total throughput without increasing speed per channel. Let's look at exciting future directions for this field. Researchers are exploring quantum Maxwell Demons, where quantum measurement and entanglement play crucial roles. Autonomous molecular sorters that don't require external control are being developed, inspired by biological molecular machines. The field of thermodynamic computing aims to build information processors that approach the Landauer limit. Sorting active matter, like swimming bacteria or self-propelled particles, presents new challenges and opportunities. Let me summarize the key takeaways from this lesson. Lab-on-chip Maxwell Demons can sort particles without doing mechanical work on the bulk fluid, using feedback control or selective forces. The thermodynamic cost appears in information processing. Measurement, decision-making, and especially memory erasure generate entropy. Landauer's principle, Q greater than or equal to kBt natural log 2 per bit, sets the fundamental thermodynamic limit. Real implementations dissipate orders of magnitude more energy than the Landauer limit due to measurement irreversibility. Biological systems use similar principles, powered by chemical energy rather than electrical energy. Here's a final thought to ponder. These lab-on-chip Maxwell Demons demonstrate that the second law of thermodynamics is not just about energy, but fundamentally about information. Information is physical. It has mass equivalent through E equals mc squared, and it has thermodynamic weight through Landauer's principle. This deep connection between information theory, thermodynamics, and statistical mechanics is one of the most profound insights of 20th century physics. And it continues to inspire new technologies, from quantum computing to synthetic biology, while deepening our fundamental understanding of the physical world.